Hello, everyone. Thank you for listening to my WOLA talk. Today, I'm going to tell you about some recent work I've been doing in the field of arithmetic property testing. So the main result I want to tell you about today is the following theorem of myself and my advisor, Yufei Zhao, which says the following. A linear invariant property is testable, where testable means testable with constant query complexity and one-sided error by an oblivious tester. So a property is testable in this way if and only if it is semi-subspace hereditary. So there's a lot of terminology to unpack in this result. So I'm going to spend the next few slides defining terms and giving a historical introduction so we can see what this result says and how it fits into the existing literature. I'm going to start with a detour through graph property testing. So one of the most classical property testing problems is the following. You're given a graph G on n vertices, where n is some very large number, and you want to determine, is G triangle-free, or is it epsilon far from triangle-free? A graph is epsilon far from triangle-free if it contains some triangles, and you can't remove all of the triangles, even if you're allowed to remove up to epsilon n squared of the edges. So one of the earliest results in property testing is the following result of Ruscia and Semeretti from 1978. Though they didn't state it in this language, what their result implies is that there's the following tester T for triangle freeness. T selects 3 random vertices of the graph and checks if they form a triangle. If they do, the tester says G is far from triangle free. If they don't, the tester says G is triangle free. So one can clearly see that if the graph is triangle free, then the tester will always say that it's triangle free. But the important part of the result is that if G is epsilon far from triangle free, then the tester T rejects the graph with some positive probability, delta, depending on epsilon. And then if we want, we can repeat this test to boost the rejection probability. A key property of this test is that the number of queries it makes is sublinear. In fact, it's constant in n, only depending on epsilon. So now let's formalize the way that this tester works. We say that a graph property P is testable if there exists an oblivious tester T that works like this. First, it's given a parameter epsilon greater than 0, and it computes some number of vertices Q that depends on this parameter. Then an oracle selects Q vertices of the graph uniformly at random, and then gives the tester access to the subgraph of G induced by those Q random vertices. The tester looks at the subgraph and then decides whether or not it thinks that the original graph has this property. And it has to meet these following guarantees. If the graph satisfies the property, then the tester always has to accept. While if the graph is epsilon far from the property, then the tester has to reject with some positive probability delta that can depend on epsilon and is greater than 0. So we can see that the Ruscia-Semeretti test from the last slide does fit in this framework. In fact, the number of vertices Q it computes is always equal to 3, independent of epsilon. So the one fundamental question in graph property testing is which graph properties are testable? Now, to be completely clear, let me define a graph property. A graph property is just a property of graphs, some collection of graphs, that does not depend on the ordering of the vertices of the graph. In other words, a property has to be preserved under graph isomorphism. So an example of something which is not a graph property is, say, graphs where the first vertex is always connected to the second vertex. But lots of other natural things are graph properties, such as being bipartite, or triangle-free, or 3-colorable, or perfect. All of these are graph properties. So let me tell you about the history of testing graph properties. We've seen the Ruscia-Semeretti result for triangle freeness. And this was generalized by some other people into the testability of some general classes of graph properties. And more work was done on this area over the years until we get to this result of Alon and Shapira from 2008, which states that all semi-hereditary graph properties are testable. Now here, a hereditary graph property is a property that's preserved by taking induced subgraphs. For example, if I have a graph which is bipartite, when I take any induced subgraph of the graph, it'll still be bipartite. So Alon and Shapiro show that all hereditary graph properties are testable, and they actually show a slightly larger class called the semi-hereditary graph properties are also testable. I'm not going to define semi-hereditary here, but it's only differs from hereditary in a minor way and some technical details. So another really exciting part of the Alon-Shapiro result is that they prove that the semi-hereditary properties are the only testable properties under the framework for testability on the last slide. So this completely solves the question, which graph properties are testable? Now, I don't have enough time to talk about the methods used to prove these results, so let me just say one sentence. There's a technique called the graph regularity method, which uses Samaretti's graph regularity lemma applied to a graph. This technique is the main technique used in all of the results on the slide in more and more advanced ways. So that's all I want to say about graph property testing. So now let me move on to the related field of arithmetic property testing. One of the most classical results in arithmetic property testing is the following. You're given a function f from a finite field vector space, fp to the n, to fp, and you want to determine, is the function linear or is the function epsilon far from linear? We say a function is epsilon far from linear if it's not linear, and you can't make it linear by changing its value on epsilon fraction of the domain at epsilon p to the n points. So a very classical test, the BLR test by Bloom, Luby, and Rubenfeld, gives a tester for linearity. The tester T works like this. It selects 2 points, x and y, in the domain uniformly at random, and then it checks if the equation f of x plus f of y equals f of x plus y is satisfied. If it is, the tester says the function is linear, and if it isn't, the tester says the function is not linear. You can clearly see that if f is linear, then the tester always accepts. And the important part of the BLR test is that if f is epsilon far from linear, then the tester T rejects with some positive probability delta depending on epsilon. And then of course we can repeat this test to boost the rejection probability. Again, this algorithm is sublinear time, it's constant query complexity. And we're going to see that it falls into a general class of oblivious testers for linear invariant properties. So let's define that formalism now. We say that a linear invariant property P is testable if there exists an oblivious tester T that works as follows. It's given epsilon greater than 0, and then computes a dimension Q, which depends on epsilon. Then an oracle selects a uniform random linear subspace of dimension Q and gives the tester access to the function f restricted to that subspace. Then the tester looks at this restricted function and determines whether or not it thinks the original function satisfied property P. And it has to decide in the following way. If f satisfies P, the tester has to accept. While if f is epsilon far from P, then the tester has to reject with probability delta depending on epsilon that's positive. We can see that the BLR test falls in this framework where Q always equals 2. If the tester is given oracle access to a 2-dimensional linear subspace, then it can look at the value of f of x, f of y, and f of x plus y, because those 3 points lie in a 2-dimensional subspace. So the natural question in arithmetic property testing is which linear invariant properties are testable? Now let me define a linear invariant property. It's a property of functions that does not depend on the choice of basis. That is, it's invariant under linear automorphisms of the domain. We can see properties like linearity, polynomiality are all linear invariant properties. But properties like being a junta is not linear invariant, since it depends on the specific basis we use. So to give you an example to keep in mind, I'm going to describe a certain class of linear invariant properties. Consider all functions on FP2, the 2-dimensional vector space. You get to decide that some of these functions are good and some of these functions are bad. Then we define the property P to be the set of all functions where every two-dimensional restriction is good. None of them are bad. So this class of properties is linear invariant. It includes, for example, linearity itself, but it also includes lots of other properties like being triangle-free, which we'll see again in a couple slides. And in fact, this simple class of two-dimensionally defined properties was not known to be testable in general until our work. So now let's move on to the main conjecture in arithmetic property testing, stated by Bhattacharya, Grigorescu, and Shapira in around 2010. They conjecture that a linear invariant property is testable if and only if it is semi-subspace hereditary. So here, subspace hereditary means what you think it means. A subspace hereditary property is a property of functions that is preserved by restricting the function to a linear subspace. All the functions we've been talking about all the properties we've been talking about so far are subspace hereditary. And of course, semi-subspace hereditary is a minor technical modification of subspace hereditary that I'm not going to talk about here. So this conjecture of Bhattacharya, Grigorescu, and Shapira is the analogous conjecture to the Alon-Shapira result in the graph property testing world. Now, this paper, which introduces the conjecture, proves the only if direction. If a property is testable, then it must be semi-subspace hereditary. Now let's explore some of the history of proving properties are testable. There's quite a lot of history on the slide, so I won't be able to cover all of it. But we already saw the BLR test for linearity. That was followed by the AKKLR test for being a low degree polynomial. Now there are quite a few general classes of testing algorithms following this, where different groups of people show that certain subclasses of the subspace hereditary properties are testable. For example, we have the result of Bhattacharya, Fisher, Hatami, and Lovet from 2013 that says a subspace hereditary property is testable if and only if it is translation invariant and also bounded complexity, which is missing from the slide. So our result from this year removes both of those restrictions, the translation invariant restriction and the bounded complexity restriction that's present in the work of Bhattacharya, Fisher, Hatami, and Lovet. We also generalize from subspace hereditary to semi-subspace hereditary, which completely resolves the conjecture of Bhattacharya, Grigorescu, and Shapira. So in the last couple minutes I have, I want to tell you about the techniques in some of these previous works and what obstacles those techniques run into and how we overcame those obstacles. So analogous to the graph property testing world, in which the graph regularity method is the main technique, all the previous work uses the arithmetic regularity method. The arithmetic regularity method is also known as higher order Fourier analysis. So in one sentence, what higher order Fourier analysis is you take a function f on fpn, and you cut up fpn into pieces using things called non-classical polynomials. And you want to do this in a way such that on each piece, f looks regular, or on almost all the pieces, f looks regular. There's quite a lot of technical work that goes into making the arithmetic regularity method work, done by all these people mentioned on this slide. So the arithmetic regularity method was used by various people to prove various partial results presented on the last slide. We add one new tool to the arithmetic regularity method. We prove a new arithmetic regularity lemma where the degree of the polynomials present in this regularity lemma is allowed to increase in an unbounded manner. This new idea allows us to remove the bounded complexity assumption that was present in all the previous works. So now let me tell you how we remove the translation invariant assumption. And this is a much more serious obstacle in previous works. So conceptually, let me just say, when you're dealing with a general subspace hereditary property, the origin of FPN plays a special role. And actually, this is a major obstacle when you're doing higher order Fourier analysis. There's an example due to Green and Sanders, which shows there are certain functions on FPN that cannot be regularized by the higher order Fourier analysis method in the neighborhood of the origin. Now, this is a serious issue because the origin of FPN plays a special role, and you can't just ignore it. Well, actually, there are two cases where you can ignore it. If you restrict your attention to translation invariant properties, like the work of Bhattacharya, Fisher, Hatami, and Lovett, then the origin no longer plays a special role. So if you only care about these restricted class of properties, then you can ignore the issue. The other way to get around this issue is that when the characteristic of the field is 2, or rather when you're working in F2 specifically, this example doesn't exist. And there, Bhattacharya, Grigorescu, and Shapira were able to solve this problem in F2 to the end, at least for the case of complexity 1 patterns. So what we do is we come up with a completely new tool that we call patching that works orthogonal to the higher order Fourier analysis method. This patching tool was initially introduced by Jacob Fox, myself, and Yufei Zhao in an earlier paper that handled the complexity 1 case. And a more involved version of this method is used in our current paper. Let me just say that this method works orthogonally to the higher order Fourier analysis method and exploits a certain Ramsey theoretic dichotomy to fill in the gaps that cannot be solved using higher order Fourier analysis. So that's all I wanted to say. I've talked about the patching technique and the new arithmetic regularity lemma, which are the 2 ingredients that we use to remove the 2 obstacles present in previous works. Thank you for listening.